So my name is Niall Douglas. If you've been to C++ conferences or watched the videos, you probably will recognize me. I've been kind of at this for a fair few years now. And here I am for the very first time at meeting C++. So it's been a great conference. I really like the food. The fact you've got food on at every single break, and there's lots of it. It's one of the best things about this conference, because all the other conferences are not quite as good. And especially getting dinner. Yeah, pizza was nice last night. So I'm here to talk about stood expected. I've already been asked by several people, am I going to talk about outcome? And I'm not. This is purely about WG21 expected as of the Toronto meeting, which was the meeting just preceding the meeting that's currently happening right now. And quite a lot of changes landed into expected. It's quite different from what it was before because of the outcome version 1 meeting. So as a result, I suppose we'll just get into it. So this is kind of a summary of WG21 type talk. So I'm going to run through a whole lot of WG21 papers and try to summarize them in a compact fashion as possible. But I'm going to list them all out to you, so if you have a whole load of questions, you can just dive into the paper perhaps during the talk and then no doubt bombard me with questions I can't possibly answer afterwards. I'm going to go into a little detail of why you might need expected. A lot of the use case for expected now, as of the current expected, is very, very, very similar to the use cases for outcome, V2. So in that sense, they're the same problem domain. They go about fixing it in different ways, obviously. I'm going to talk a little about the current proposed expected. If you looked at expected a year ago, it is now quite different from what it was before. There's a lot less in it, but there's also more. So I'll have to cover that to go and give you some idea. I've already been asked today what's happened to Monadic bind. In fact, I've been asked it twice. It's gone out of outcome, it's gone out of expected. The reason why is because a separate paper is now covering the Monadic extensions, and I will do the world's worst summary of those. You can go look at the paper if you really want to know a whole lot more, but at least they're there, and you'll get some idea of where things are going. Next thing is expected operators. So there's a raft of operators to save on boilerplate when you're working with expected. That's another paper again, and I will cover those. This keeps getting asked. I got asked this at ACCU last April. I got asked this on multiple occasions. So how do you implement a construction of objects without ever throwing any C++ exceptions, also allowing failure and purely returning failure through expected/outcome? So I actually had to invent this due to my AFIO library, which hopefully will become the file IOTS next summer when I go propose it, and hopefully they'll okay it. And I had a problem where I needed to generically construct some arbitrary unknown object which could or may or may not be an expected/outcome based construction system. So I had to come up with some metaprogramming to let me do that. As a result, what I propose here, what I show you here is a little bit convoluted, but it's very, very flexible. So that will give you an idea of how to do it, and that will finally, hopefully, make everyone who keeps asking me that question be happy, with a bit of luck. And then finally, I don't know if we'll get onto this. Last item, if time runs out, I'm happy to skip it, because you can go to my ACCU talk in April 2018 if the ACCU accept my talk proposal. But if they do, I will be getting into Outcome V2, which will hopefully be a full boost library by that point, because the second peer review hopefully will be the end of January. And I will dive into the problems with expected. But if there is a bit of time, I might quickly skip over them. I don't talk about solutions. Obviously, outcome solves them, a whole load of it, but that's okay. So relevant WG21 papers. So this is just a long, long list. Some of these papers are quite old. You can tell by the sequence number that 157 into the new P number system of naming them is obviously well before 323 for the second one. But what I did instead was I added the dates, so to give you some idea of when things began. This is actually inaccurate. This is only for the P paper. The expected proposal probably started about 2012 in terms of N papers. So I just put those in so you can get some notion of the timeline of, you know, you're here 2016 and so on, to give you an idea of the maturity of the papers. You'll see me up here. This was literally in the mailing that just went out. I expect this to be completely ignored by the meeting that's currently happening, simply because I'm not physically there to champion it. So that's fine. I only wanted to get it out there so people knew, so I felt happy. But I expected none of that will get taken notice of. I also expect no one to take any notice of this either, but it's there for you to go read. And then finally, this is a really, really new paper. This is Vicente's bridging proposal to bridge outcome and expected into one and the same. The reason why is because outcome is going to become the Boost peer review chosen way of doing this, and is not going to be the WG21 way of doing this. So there is going to be a problem when you have code that's using the Boost outcome, which is not quite the same as expected. And Vicente came up with this series of concepts to bridge the two together, so you'll be able to write code that works with both. They'll just seamlessly interoperate. And I've literally just implemented that into outcome about 20 minutes ago. So it first started compiling about 20 minutes ago. So it's now in, and I can actually say, if Vicente, if you're watching, I've implemented it. So it's done. It took me a while. It was actually surprisingly painful because do you know what the problem was? It was actually GCC rather than Microsoft's compiler. Microsoft compiler actually just worked, but GCC was being a real pain. So anyway, why might you need expected? So this here is a graph which I appreciate that people at the back probably can't read very easily. I already did a font size check, and I know that you probably can't. But I wasn't going to go and redo the graph, so tough. So the idea behind this is that this is a really, really terrible benchmark that means nothing, and you should read nothing into it. But the idea is that you return up 10 stack frames. So you unwind 10 stack frames in x64, and how many CPU cycles might you take? And here's GCC 7.2 with exceptions disabled, GCC 7.2, GCC 7.2 with link time optimization on, Clang 5. This is the very latest version of Visual Studio with no exceptions, with link time code generation. And then just for a bit of a laugh, I threw an Xcode 8.2, which is actually for outcome V1. These are all actually outcome, but you're going to get exactly the same results for expected. And the first thing you should really notice is that over here is a log graph. So 100 cycles here, and that's probably about 30,000 cycles for the expected throwing case. So as you can see, the yellow is expected. So that is just a notion of how expensive throwing and catching an exception is on a table-based EH implementation. And if this kind of thing matters to you, then you're going to be interested in expected. If you couldn't care less, then you're not. And it's a bit like what Kate was saying this morning in her keynote. Banning exceptions comes with a cost of increased complexity, but sometimes you need to pay for that increased complexity if you want your code to run on a fixed latency and a fixed bound of time. There's also some other benefits to do with auditing as well. So you pay for what you use, you know. So I appreciate as well that these may or may not be read. Can people at the back read the writing on this? Okay, cool. So these are some flow charts, because I really don't want anyone to think that you should be using expected/outcome unless you really, really ought to be using it, so don't just use it because it's cool. So the first thing is, are you regularly passing failure up the stack, so to be handled? So are you not handling failure locally? If so, is occasional failure likely? If so, use expected. If occasional failure is not likely, use C++ exception throws. The reason for this is because expected-based code or outcome-based code sacrifices a certain amount of overhead during the successful code execution in order to have really, really predictable failure handling times. So you're handling a little bit of something in order to get predictability for failure. C++ exception throws on a table-based system implementation is exactly the opposite. So they make it go as fast as possible for the successful case, and then they have really, really terrible times, execution times, completely unpredictable for the failure case. So this is why this would be a useful thing to follow. Similarly, worst-case execution bounded time are important to you. If they're not, use C++ exceptions. If they are, is your compiler using a table-based EH? People ask which compilers don't nowadays. It's actually Microsoft on 32-bit still uses a non-table-based EH implementation. And so failure for that's really, really fast and really predictable. It's just as fast as being successful. On the other hand, if you run anything else any of the other major compilers on x64, you are now using a table-based system. So if you are, then you might want to consider using expected. Otherwise, C++ exception throws. Finally, if your answer to any of these questions is yes, then you might want to think about expected. If you're answering no to all of these questions, you probably don't need it and don't want it. I should say, companies that ban the use of exception throws, they get really bad press within the C++ community. I'm a contractor. I work various gigs for hourly pay. And I've seen a lot of big organizations insist on turning them off. And I don't think they do that without thinking it through. I think they get a lot of bad press. Like Google, for example, say that you can't use C++ exception throws in their C++. And they get a whole lot of grief from the C++ community for it. But I think the cost of fully testing your code that throws exceptions is quite high. And if the organization has decided as an organization we're just not going to expend that kind of resources, I think that's up to each organization to make. I think there's a cost benefit in there. And you have to bear in mind, developer time is expensive. Most developers are earning $50, $60 an hour at least. Of course, if you're in a games environment or a high-frequency trading environment, you almost certainly have C++ exceptions off anyway. And if you do, and you want to handle failure, expect it is an excellent place to start looking at. And finally, the most interesting one, of course, is that if you are adding exception-throwing code into an older code base, which is not written to be exception-safe, expect it is a really, really snazzy tool. So one of the really interesting things is if you've got some mature, cute code base that is completely hates exceptions, and if you can't do them, and you want to use some parts of the C++ 17 STL like std variant, which may or may not throw an exception, depending on how you use it, you might want to wrap that up in something like expected, and then you can transport expected through Qt code completely safely. And that is a very useful thing to think about. So any questions so far? In the middle. Now, I might add, I've been told to tell you that there is a microphone, but... I
don't know if this is too big a question to answer, but can you elaborate on why the table-based exception handling is so much different than the other exception implementation mechanism?
So the question was, can I elaborate on why the table-based exception handling mechanism is so much different from the other exception handling mechanism? So, right, compiler internals. So what happens in a table-based exception handling system is that when an exception gets thrown, you run into the runtime. The runtime will go look at the stack frame, so it will look at the current stack point, it will look at the different return addresses running up the stack as it goes, and it will basically do a search of the tables that were compiled in by the compiler at compile time, and it will index through to figure out which stack frame unwind calls to go and call. It will then call each of those in turn. Now, if you think about it, that sounds fine, but if you think about it as well, these are all cold cache items, right? So if you come along, you're going to go and pull something from main memory. That may even have to be brought in from swap file, right? And it's going to hang until it goes and pulls. These are really far away from normal execution code, right? They're often cold space. So you're going to be hanging in a whole load while you're going and waiting and pulling this stuff in. You've then got to do a whole lot of pointer dereferencing. So you've got to dereference a pointer, then jump through that, which tends to be pretty slow. And you may have to do this 2 or 3 or 4 or 5, 6 times per frame unwound. And if you actually add it adds up to several thousand CPU cycles on average per frame unwound, simply because modern CPUs, they're really bad at, they speculatively go off and execute lots of branches of code, and they throw away the ones that they don't actually follow. And that makes them really, really slow when it comes, relatively speaking, when they can't predict where the future is going to be. And this wasn't the case, say, 20 years ago. So I remember an old ARM2, you wanted to dereference pointers all the time because it was a different stage in the pipeline execution. It was actually faster than accessing a cache line that was near your current place of execution. So, CPUs change, hardware changes, and that's the reason why. I did actually mention to some compiler vendors about how slow it was, and people were like, ooh, that's really, really surprising. But at the same time, we haven't actually benchmarked it since the late 2000s. And we're not surprised, because modern CPUs are like that. Any other questions? Okay. So this is the, what's the current proposed expected? And if you want to know more, you want to go read the paper P0323R3. So there has been some changes. Yeah. Expected, I don't know how familiar, of course, you all are with std variant as in C++ 17. Std expected fixes some of the unfortunate design decisions in std variant. So one of the big problems with std variant is that it does not have a strong never empty guarantee, which is really unfortunate. Anthony Williams has some papers written about how you'd go about getting existing std variant to be never empty guaranteed. And a lot of them were very feasible, but unfortunately that ship has sailed, so that's gone. Std variant, unfortunately, will not sometimes become empty, even though it's advertised that it never will. And you'll get this valueless by exception flag suddenly turning true. Now, expected because it comes along a bit later than that, has not replicated that mistake. It has used Anthony's ideas to solve the never empty problem. So that's the first thing that's changed. The second thing is that it has an API of an optional rather than, so the T state being expected and E state being unexpected. So it looks a bit like a variant in terms of that it can have a T or an E and it's stored into the same physical space. Maybe. That's not actually specified by the specification. But it has an API of an optional. I personally think that's a huge mistake. I think that this thing should not have that, but I am in a tiny, tiny minority on the committee. I'm not even on the committee yet, but I will be next year, hopefully. But certainly, I am in a very small minority on that. But I would say that most of the Boost folk during the Boost peer review probably came around, I think, on average, to agreeing that the choice to adopt an optional, expected is not an optional plus an error state. Everyone thinks it should be, especially in the committee. But it actually isn't, because you don't ever use it for that. And I might get into the problems later on, or else I've got to wait until ACCU. Okay, so I will just give you a quick synopsis in code. It's dead simple. Expected is ridiculously easy in some respects. Does anyone not know what this requires clause is? Put your hand up. Okay, right. So this is coming in C++20. You will be able to specify requirements for template types. So you can say that this template will not be instantiated by the compiler if the requirements is no throw move constructible E and is not void E are not met. So if those requirements are not met, the compiler will refuse to instantiate this template and you'll get a compile time error. So this saves you having to do a spin A and a whole lot of other of the usual crap that we have to put up with in earlier versions of C++. This is just so much better. Clang already implements this from trunk. GCC 7 has a reasonably working implementation with a number of bugs. But no, it's, and I think there's an internal build of Microsoft's compiler which is floating around by email if you ask the developers really, really nicely that implements this as well. But obviously you shouldn't be shipping it in production code yet. But no, it's great. It so tidies up writing this sort of stuff. No more macros, fewer macros. Class expected, anyway, has a value type equal to T, the same as optional. It has the same usual ways of constructing the T, assignment, swap, the usual sort of stuff that you always get. Initializer, lists. I didn't bother listing them out here because it would take too long. It's just the same as optional. It has a pointer indirection operator. It has a star operator. It has a comparison to bool. It has a has value. It has a value accessor. I've only listed one here, but there's actually, of course, 4. So there's one that returns an R value type, there's a const R value type, and a const L value type. There's also a value OR operator. I don't know why that's actually still in the expected proposal. I just checked because I thought that surely had been stripped. But no, I checked last night and it's definitely still there. I don't know why that hasn't gone away yet. I'll explain why later in the talk. And this up until now is basically the same as optional. So here's the additions. You have an error type E, and you have an expected with unexpected type E. So this is type sugar. It says, please construct an unexpected addition of myself. And then over here, you have an observer for error. Down here, I have the weasel words, template deduced unexpected type sugar. This, if you're familiar with template deduction guides, which are a new feature coming in C++ 17, makes total sense. But I didn't put it up, and I'll tell you why. It's because I guarantee you that a whole lot of you would ask questions about it, and I'd have to explain template deduction syntax. And it's really confusing until you get it. So when you're looking at it initially and you're trying to write the stuff, and I can say this from personal testimony, you write out the code, and a stupid compiler will not compile it properly. And you keep plugging at it and like changing bits, and you're sitting there going, what the hell? And then suddenly it clicks in your head of what they were looking for, you write it out, and it works. Unless, of course, you're in GCC, in which case it blows up because there are bugs in the implementation. And I had to go onto Stack Overflow, and I said, shouldn't this compile? And they went, oh yeah, GCC parsing bug. So I'm like, okay. But no, anyway, there's a set of stuff, and I'm not going to explain it because I don't want to have to answer questions on it. But what I will say is go to the paper if you're really interested, and it basically is a way of wrapping up an E-type into a structure. You then feed that as type sugar into the expected implementation, and it will construct an unexpected addition of itself, because the default constructor converts from an expected addition. Apart from the template deduction guides, any questions? At the back.
Exactly about the error thingy, the E-type. Why do you have to wrap it? Why can't you just have two constructors, one that constructs from the value and the other that constructs from the error?
So the question is
Only they can both be constructed from the same source type in such situation. Is that because of that?
So the question is why can't the constructors construct from both T and E when the construction is unambiguous, is basically what you're saying. Guess what outcome does? And the reason why the standard committee one does not do that is because the standard committee does not like implicit conversion. They're actually still thinking about disabling the implicit construction from T, so you will not be able to implicitly construct an expected at all without having to mark it up. So that will actually be even the opposite direction of what you're just saying. So you're shaking your head right now. The committee is very scared, and rightly so, of implicit construction. So they have to set a higher bar than even the Boost libraries do, or we do in our own code, because you don't know what crazy things people are doing with code out there. And I think bitter experience has shown that they really want you to really specify what you mean rather than the compiler deducing stuff. Now, I would say during the Boost peer review, the Boost community came together, and after quite a lot of debate, there was like 800 plus submissions to the Boost peer review, first one. And in the discussion, we came up with a set of rules for really, really conservative rules for when we're allowing implicit construction from T or E. Basically, T and E have to be completely and utterly unrelated to one another in every possible way, and then it will turn itself on. If there's even a merest hint that they could possibly be confused, all of the implicit constructors totally disable, and you have to specify out what you want. So that's doable. It's totally doable, but that's not the way the committee are currently going. There's a question at the front.
Does the proposal support references?
The question is does the proposal support references? Currently, no. So you have to wrap it up in the standard, reference wrapper, exactly, if you want to use it with references. Everyone else happy? Cool. Okay, I'll show you an example of usage, get you some notion of how it works. I literally have pulled this from Vicente's paper. So, firstly, what we do is we define an error type, and we're going to call it arithmetic error C. We're going to define this error type, which is divide by 0, another by not integer division, and integer divide overflows. We've given some examples over here to give you an idea of what that means. You then declare an expected, which can return either an int or an arithmetic error C called safe divide, which takes I and j. Is 0, we return this. If this, return this. Am I getting disconnected? I don't know. And if this could happen, we return that. And then at the end, if all successful, we return I divided by j. Does that all make sense? You might notice just how much you have to type here. There's an awful lot of typing with expected. Guess what one of my problems with expected is? So here's another use case. So assuming the function you just saw beforehand, we now have a new function called f1 that's returning a double and also has the same arithmetic rc. We have a double I int j int k, and what we're going to do is call the safe divide that we just saw beforehand. We're going to shove it into an auto, which was the expected int arithmetic rc. If not q, because you can test these things for Boolean truth or false, and if it's false, it means there's an error in it, then we extract the error using that observer, we wrap it into an expected, and we return it, which will then be implicitly converted by expected into a state of arithmetic RC. So in other words, we're propagating it out. Otherwise, we dereference the value that was in the return from safe divide, we add it to I, and we return that as a positive outcome. Is that all okay? Your faces indicate that's fine. I know we've kind of gone through this how many times now? This is my second one. Yeah, so here's the thing. You have to put this throughout your code all the time. You end up writing this so frequently, like constantly. I have written, obviously, AFIO, which does a ton load of this, and you end up wrapping this into a macro. Because rather than having to constantly do this again and again and again, just write a macro that saves you having to type it out. Now, there are two solutions in the works. This is a paper proposal by me. operator try. I think it has a snowball's chance in hell of getting adopted. Here's the Vicenti's one, which basically adds the monadic operators. I'm going to cover those shortly. The reason why operator try has probably very little chance is because it's very, very, very unambitious, at least at the beginning. And then I add on to the end, well, why don't we just get rid of C preprocessor macros by implementing C++ native macros built into the language? And I already know that WG21 members looked at it and just went, oh, God, no. So they'd actually prefer the C preprocessor to remain rather than us going off and putting macros. So as someone earlier to me in the conference said, forced inlined functions, which is another way of putting them. Okay, so an awful lot of people ask me about the monadic functional programming stuff. And I'm going to be really controversial and say there's about 12% of the C++ using community who get really, 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 really passionate about it. And the other 87% couldn't give an arse. They really couldn't. And on the basis of that, the Boost peer review is pretty clear that the monadic stuff is such a small number of people who are really, really, really keen on it that they can go off and implement their own thing on top, and it shouldn't really be shipped as a default implementation. So we haven't done it. But if this paper were ever to be made into the standard, and this will be after C++ 20, almost for certain, then this would let you work with any expected like object, which includes outcome, or anything you define that quacks and talks like a monad-ish, and it would automatically plug into these functional operators. So it's kind of clever, but it's definitely not coming in C++ 20 by any stretch. I'm not going to explain any of these. If you are familiar with functional programming, you'll instantly get that this is a list of the standard monadic operators. I'm not going to take any questions on it because I have to look it up myself every time I need to remember what all of that means. But to people who are really keen on Haskell and functional programming, this should all just make sense apparently. I still struggle with it at times, I have to admit. If you want to know more, obviously read the paper. It goes into quite a bit more detail. I'm simply going to show you what these expand into in C++, and that will hopefully explain it for those who don't instantly get the syntax. So this is one way that we would hide boilerplate in expected. So you might remember beforehand we had a series of if statements. You do a operation or a call a function that returns an expected. You then have to check it, and then you have to propagate the error. So another way of doing it is to write this out functionally. And what you do here is you do the bind operation. And I will explain in a minute, but not quite now, what the bind operation is. So what we do is we call the safe divide function that we had earlier on. If that returns something successful, it will call this callable here, which is this lambda. This lambda then calls another bind operation calling the same safe divide but with different parameters. And if it's successful, it will call this lambda here. This lambda then goes and adds Q1 and Q2, returns it back out, and that will correctly return an expected int arithmetic ARC. If either of these safe divides fails, it will automatically propagate the arithmetic ARC back out. Okay, so this saves you having to write all the if statements, but it's exactly the same. It's equivalent in every way. So the bind operation, as far as I could tell from Vicenti's paper, and I apologize now if Vicenti's about to send me an email saying you got that wrong and it should be this, in which case I'll add an errata to the YouTube video like I did last time. What it means here is that if expression, so if the expression was successful, then we return the unwrap of the invocation of the contents of the expression. So you call the lambda with the contents of value, and you unwrap any expected that might happen to come out of it. Otherwise, you return, propagate the error. So you pull out the error, and you return it as expected. So that is that operation. I believe that's all I'm going to say on the matter. If you're really, really into functional programming, you should go look at the paper. The paper's been around now for a year, 2 years or something. An awful lot of people on Reddit and on the committee, on Boost, long list of people get really, really passionate about this stuff. Well, this is the most mature set of monadic operations being added to C++, or rather proposed to be added. I think there was only a paper just this WG21 meeting where someone wanted to add monadic operations directly to optional. But you see, if this went through, these things are adaptive. So monad bind will accept an optional, it'll accept an expected, it'll accept an outcome, it'll expect anything that matches the concept of a monadish type. So you can feed anything to it, including your own types. So, any questions on that one? So you all just got it, did you? Cool. I don't get that stuff. All right, so more boilerplate saving. So this is a brand new thing. This is what Vicente came up with to allow outcome and expected to work together and any other arbitrary type of your design. You might know that Facebook has its own expected implementation and its own optional implementation, and they've been doing all sorts of fun things to it, like adding in coroutine support into it. I know Google have their own implementation of both optional and expected, and they've also been adding their own custom extensions into it as well. So it's not just Boost, not just us. There's a whole long list of people out there who are using expected-ish type things already. They already have their own implementation. And so what we need is a system to bind them all together. So we're about to jump into some C++ 20 concepts, I guess. Not too hard. Obviously, the paper is P0786. So the two concepts that are proposed by the paper are really, really super simple. You have a value or error concept, and this accepts any type which has a .hasValue observer, a .value observer, and a .error observer. And the classic one there is expected T. It doesn't matter what it is. You just say, feed it that, and it'll automatically recognize it. The other concept is value or none, and this accepts any type which has hasValue and value, e.g. optional T. You might notice that expected will match this and match this. So because expected you just don't recognize the fact it has an error, it will fit into the value or none concept. Okay, dead simple. So if you can fulfill those two concepts, or one or both, then you get these operators built in. So the operator try paper, which I mentioned just beforehand, was written assuming that this paper would be in existence with these concepts. Vicente's got a notion of doing something with operator question mark. I think he's literally discussing it in the WG21 meeting that's happening during this conference. So I don't know any more than that, but I have written out what he told me he had a notion for. So you're actually kind of almost having precognitions or something of what might be happening, or not, I don't know. There's a value or operator, a value or throw, error or check error. These are all boilerplate saving items. So the first things first. This is the try or question mark operator, and I have both forms listed at the bottom, as you can see. It takes this simple form. So if you have some expression that returns some expected TE, the boilerplate this will be expanded out. So if E1 has value, return the E1 error. Otherwise, we extract out the value by move into TV1. And that boilerplate would be eliminated and replaced with, under the try proposal, try that. So it basically expands into exactly this stuff here. If it's an operator question mark, then just like Swift, because that was inspired by Swift, you put a question mark after the function name, which is a returning of expected or anything matching a value or error concept, and it simply expands out the value. I still seem to have your attention, so that looks good. Does that seem all right to everybody? Makes sense? Okay, so this is the value or operator. So similarly, here's your concept, value or none. Here's your class T, here's your value or, which is a free function. It takes a concept matching X. It takes a class T of arbitrary TV. It will simply ask, do you have a value? If you have a value, return the value. Otherwise, return the class, the V value that's put in. And here's your use case. Expected TE equals expression. V0 will be whatever or value you choose. You simply then type value or. So if E1 was successful, we get the value from it. Otherwise, we substitute V0 value. Okay, I see a hand down at the back.
Why don't you just, instead of using has value, basically could use the conversion to bool and the referencing operator, so it works with pointers as well?
So the question is why don't we just use the Boolean test and the dereferencing operator so that it works with pointers as well? I don't know, I didn't write the paper. I would say that probably, and I'm just going to take a complete hazard guess here, is that the use of these with a pointer hasn't been fully thought through yet, because this is quite an early paper.
How we did this, because sometimes we, instead of passing an optional into a generic function, we sometimes pass a const pointer, which sometimes is handy if you want to pass something like a const optional, and then you just pass in a const pointer and everything else works the same way. It's quite nice that optional is quite similar in this way. And
so he was making a point basically that they have code already that basically does this already in their own thing, and he feels very positive about how wonderful this idiom is. I'm sure that as the proposal evolves and people get to look at it a bit more, I don't doubt that will be considered. But it's a bit like with the explicit construction for expected. The committee may be very conservative on that. I mean, what's safe in your code base may not be safe in the wild, wide west of all C++ users in the world. Anything else? No? Okay. So, value or throw. This is Vicente's solution to, I should explain it a little. Outcome has some interesting boilerplate saving stuff that saves you having to type anything. So you can program it to go off and throw custom exceptions on the basis of you doing various stuff without you having to type anything. So Vicente was like, well, we can just come up with this value or throw thing, which basically does the same thing. And I'm like, Vicente, but you have to type value or throw all the time, which kind of defeats the purpose, in my opinion. On the other hand, what I will say is that value or throw is super clear that when you're doing something that this thing might throw. So that has the advantage, and that probably will make the committee very happy that the programmer is literally writing out value or throw. So value or throw is very simple. Once again, it goes has value, and here's for the value or none concept, by the way. So this could be like optional. Has value. If it is, it gets the value out. Otherwise, it throws the E type, which you passed in here, default constructed. If it's a value or error concept, then again you get has value, returns the value. Otherwise, it throws E, but constructing it with the value of the current error. Here's an example of usage. T with std error code is the E value. If this expression has the value T, the T will be extracted. Otherwise, it will throw system error, so that would be std system error, taking the std error code that was returned back as its input parameter, and that will get propagated up the stack unwind. Does that make sense to everybody? Okay, question at the back.
Is b.error, is that b correct, or is that supposed to be an X?
Sorry, say again?
b.error in the lower line here below? Yeah, b.
Oh. So the observation is that shouldn't this be x.error? And yes, it should. v.error is incorrect. This just goes to show how tired my eyes are. I can't see anymore. I used to wear glasses, but my eyesight's going out longer and longer, so I can't really wear them with a computer anymore. And that's the kind of mistake you get. Thank you very much for spotting it. Everyone else happy enough? Okay. So I'm kind of getting a little bored of these now, so I'm just going to skip right through this. This is error or, and it's exactly the same as value or. The difference is that it extracts an error, or it returns the V. It basically does exactly the same as value or, but supplied with an error value. Everyone happy? Yeah, cool. This is check error. I don't really get the point of this particular operator, but I didn't write the paper, so what can you say? So the idea behind this is that instead of typing out this very small amount of boilerplate, that you would end up writing another if statement with the same thing. And I don't know, it's just in my head. You might as well just type out the boilerplate, do you know? It doesn't really save you anything to do this. I suppose the only thing you could say is that maybe you could use this as a customization point, maybe, and maybe you could come along and you could change what check error means for some arbitrary combination of certain types. But I don't get this as a boilerplate saving thing at all. But there you go. Okay, before we move on to the next section, any questions? Oh, cool, okay. So I think we're actually doing a little bit better of time than I was expecting. I was expecting lots more questions, but we'll see what happens. So this is going to be a bit slow moving. As I say, I came up with this for the AFIO library because I had a problem What I'm doing, you see, in AFIO is it's meant to act as a prototype for the stud2 containers, which I have in mind, which would be quite similar to what Alistair Meredith did for CPVCon. So if you know about John Lakes' allocators, in fact, he only had to talk about it yesterday, you'll have seen lots of swirling heat maps, I would imagine, if he did the same presentation as before, showing different performance. Great stuff. Alistair's then taken this out. He also works at Bloomberg, and he took it out to remove allocators from the container type system. So the idea is for stud2, for this next generation of STL, that you would not have the allocator in the type of the container, which I think is one of the best ideas I've heard in years. I don't like the rest of his proposal. I think the rest of his proposal is awful. But that particular point, that key part of eliminating allocators from the containers, I think is a spectacularly good idea. And that's exactly what AFIO does as well. So one of the reasons why I need to know how to generically construct arbitrary objects is because AFIO gives you access to the virtual memory subsystem. So you can page pages in and out, you can allocate them, you've got much finer grained control over the memory subsystem. And because of that, you can now implement a set of containers which are aware of the fact you're running on a virtualized memory subsystem and the fact you can page stuff in and out. You can say, well, I'm not going to use this 4K page for the next while, so kick it out temporarily. And you can bring stuff in. And there's a long list of really, really interesting new algorithms we can do. So for example, you can take an array, and if it has a trivially copyable type, you can expand that array as arbitrarily as you want with no memory copying, because what you do is you simply re-memory map the same storage, which is backed by a file, which is actually something that doesn't exist, it purely exists in the mind of the kernel, and you simply expand it with no actual memory copying, which is an enormous performance improvement if your type is trivially copyable. So this is why I needed some generic system for constructing arbitrary unknown types from metaprogramming, which could be purely expected based. So this is what I came up with, and I appreciate it's a little convoluted, but it's good, so we'll see where we go with it. The prerequisites for this is that your type must be movable. Your type moves must be cheap. Obviously, you can replace movable with copyable, so long as copyable is cheap. You need to not mind a bit of metaprogramming, because it is slightly awkward to use, and you don't mind typing more. So it's one of the great things about C++ is that it's really, really powerful, but generally speaking, if you want to do something right, or if you want to do something weird, you have to type a whole load more stuff. I remember saying that to Bjarne, and he seemed to feel that was also true. So first thing you need to do, if you're going to implement a 100% expected-based, never ever throwing any exceptions constructor, is you need to break your construction up into two phases. So it's kind of weird because Kate this morning was telling you not to do any of what I'm just about to talk about. But I respectfully disagree with Kate for some certain circumstances. I would say in a lot of lower level code, it makes an awful lot of sense to have an all const per phase. So the all const per phase lets the compiler do the bit which is const able as ideally as possible, and then your second stage of construction will do all of the non-const per stuff, so the stuff that has to happen at runtime. Obviously, the all const per phase, being const per, can never ever fail. If it fails, it will not compile. So if it compiles, it works. And then what you do is in your second stage, you have the ability to fail returning an expected. Step 2 is you tell the metaprogramming how to construct your particular object. And now what you get is that end users do this lovely construct, which is a free function. Well, it looks like a free function, but it's not. It's actually a type. So the type is called construct. Foo is the type that you want to construct. You put your arguments for construction in between curly brackets, and then you add on a set of normal brackets at the end. I know that looks really non-intuitive, which is why I color-coded it. This takes advantage of a C++14 feature, which is default member initialization. So what you can now do in C++14 is when you're writing out the class definition, you can say that if nobody else initializes this member variable, please initialize it to this, some arbitrary, put little curly brackets after it. And this actually, if you think about it, is a form of defaulted parameters. So if you use one of these types as a set of parameters to be fed to a construction of an object, by defaulting the member variables to some default value, you get the same effect as defaulted parameters to a constructor. But I agree that it's kind of really annoying that you have this stupid set of brackets at the end. If you could put this here, and I'll explain that you could do that, but there's consequences to it. I'll get to that at the end. Is that okay so far? I'm about to go and show you actual code of implementation. So, okay. So here is a strictly reduced, terribly reduced file handle taken from AFIO. And I only borrowed this because I needed something quick to come up with. And this is a really super simplified edition of the actual real code. So here's your file handle at the top. The file descriptor is an int on POSIX, and we default member initialize it to -1, which is an invalid, I think it's a guaranteed invalid file descriptor on POSIX. We also keep a struct stat. The reason why we do that is because AFIO implements race-free file system. And for that, we need to know what the inode and developer device node or IDs are of the particular file descriptor. So when we're doing operations later on, we can compare. So we need to take a copy of that, and we don't actually hold a full stat. We actually only hold the 2 bits. But for here, just assume that we do keep a full stat. Obviously, constructing this or initializing this is going to be something that could fail. This could also be something that's going to fail in a real-world constructor. So there's 2 stages here. Down here, we have a phase 1 private const expr constructor. It appears to do nothing, but what it actually does is, because it's marked const expr, if you try to put any default member initializations here which are not const expr, because this is const expr, the compiler will barf out and say you can't do that default member initialization when the constructor is const expr. So instead of defaulting it, what you do is you actually set it even though it does nothing, or it appears to do nothing. So that's the trick that's being done here. Here's your phase 2, which of course is going to be a static member constructor function. This has been the case since Qt days and well before. So we declare something that returns expected. So in the successful case, it's going to be a file handle. In the failure case, it's going to be a std error code. The constructor's name is going to be file. We'll put in a path type path, and the mode will be defaulted off to read. And of course, we'll say it's no except, so it can't throw. So all errors will come out using expected. So far, so good? Okay. So this is phase 2. If you remember, phase 1 initialized the file descriptor to -1 and the stat structure to all bits 0. So here's the exact same thing as we saw earlier. Now what we do is we do phase 1, which is simply to construct a file handle. It doesn't have to have anything else because it's a really, really simple default member variable initialized structure. Phase 2 consists of trying to open the path that was passed through. You can see here it's doing a conversion to UTF-8. This is interestingly a bug, now that I look at it, and I really wish I'd noticed it sooner, because that I think can throw if it's a invalid UTF sequence. And if that's the case, we would of course get std terminate being called because this is no except. But let's just pretend that isn't there. If that fails, we're going to return an unexpected made up of an error code made up of errno, which was of course set by open. And we're going to say system category because system category is the category for system error code on POSIX and Windows. So if you were on Windows, system category would be the Win32 error code domain. On POSIX, it's the POSIX error code domain. So that's why we use system category. We do the stat struct in it, which is not mentioned here for brevity. And at the end, you'll see that there's this very curious initializer list-based form of return. I should probably explain why. The problem is that when you're returning a ret, which is here a file handle, and that is then being implicitly constructed into an expected, historically there were some really weird compiler quirks in there. And you would have this weird thing where if you wrote it one way, you would find one of the compilers would refuse to compile it, but all the other ones were happy. But then if you changed it slightly, that compiler would now work, but then one of the other compilers would blow up. Now, the most recent editions of all of the compilers do this correctly, but it was kind of one of those strange things that made me think, because if file handle is move only, then you need to make sure it moves. But if you write down just std move ret here without the curly braces, then clang tidy will complain at you and say, oh, you can't use std move to return from a function. Because the stupid thing hasn't realized that we're not actually returning a file handle, it's incorrect semantics. Just assume that std move with something at the end is bad. So it doesn't know any better. So partially to shut up clang tidy, and partially because this works correctly in all compilers that I'm aware of, what we do is we wrap it into an initializer list. That then gets fed into expected with the file handle std code. That correctly moves ret without causing any problems and is efficient and works. So that's my suggested form. It also has a nice tendency of indicating that we're not actually returning a ret. In other words, we're not returning a file handle. We're returning something that implicitly constructs from file handle. So that's my suggested form. That's what I've ended up using in all of my own code. It's at least quick to type, and yet descriptive, I find. So here we now define the construct type shim, as it were. It's dead simple. This is the default implementation. It would be somewhere within your code. It takes some class T. It has a call operator on it, which has a default implementation of simply doing a static assert. You forgot to specialize for this type T. In case people are wondering why am I doing an isSameTT value, which seems like it will always be false. That is correct. It will always be false. But what it does do is it means that the static assert becomes template dependent. If you did not have that there, it would always fire and always produce the static assert failure, which then means you can't compile a program. So by putting in this completely redundant and stupid TT thing, you make this only fire when the template gets instantiated. Now, a lot of people use size of T here, and I personally find that that's a bit risky, because how do you know that your T has any size? And for completely generic code, maybe it doesn't. Maybe it will be 0. People then do other weird things, like putting a decal type with other stuff, and then you start finding yourself typing a whole load of extra code. So I don't know, I'm sure somebody will come up to me afterwards and say that this is a really terrible way of doing it, and they've got a much shorter, faster, and more accurate way of doing it, and I look forward to hearing those. Okay, pardon me. So the next step you have to do is that you've previously had a file handle. You need to tell construct about file handle. So we do a partial specialization of the construct type with file handle, and in that, we declare the arguments for construction of a file handle. So here's your path type, and here's your mode. You'll notice here that we've defaulted read, mode to read, exactly the same as the static initializing member function. Any other args would be, then I put default initialized in curly brackets, follow here. And then down here for your call operator, you have a thing returning your expected, and all you simply do is you simply call the static member function that we had before, moving the path, and now it suddenly occurs to me that I never bothered bringing in the mode. So there should be a comma mode just there, and I will fix that in the slides before I upload them. Any questions about that? Yes, one at the back.
Just concerning the static assert, with a standard type, isn't it that even a type which has no members has at least the size of 1 byte?
So the question is it not the case that any type, even if it has no members, has a size of at least 1 byte? Would anyone else like to go and answer that? I see Jonathan over here.
Yes, this is true, but if you have a class forward declaration, size of that class between 0 is possible.
Okay, so Jonathan answers that yes, it is true that it will always be non-zero, but...
But if the class is not defined yet, only forward declared, the size may be 0.
And he says that if the class has only been forward declared and not fully defined yet, then it may have size of 0.
Okay, then just one more question. I'm doing this exactly the same stuff without the size T, the size of in general, if I want to do something like that. But somebody told me, I'm not sure if it's true, that's the question, that should be, or is undefined behavior, or unspecified, I don't know. Is that true? Or...
Say it again, please.
Just what you did there with the static assert. Someone told me, I'm doing it the same way, someone told me this is undefined behavior if you're depending on the T there. I'm not sure if it is. It's just a question. Is it?
So the question is that he seems to feel that somebody told him that that this is undefined behavior. So when the type that's being input here is a templated type, that the static assert and the use of this is undefined behavior. I'd be really stunned if that were the case. But I don't know, I'm not a language lawyer, so maybe, I'll put it this way, there's an awful lot of boost code that's doing it. Any other questions? Yes, Jonathan.
That you
parentheses at the end to invoke the function call operator. So like an implicit conversion operator that does the same as the function call operator.
So Jonathan suggests, have I considered using a implicit construction converter so that one does not have to have the call operator? No, I had not considered this. We'll have to speak after, because that's not something I'm going to answer lest I make a fool of myself in front of a videotaped thing. I've learned this. Don't answer stuff you don't know when you're being videotaped. That way then you can preserve the illusion that you know everything. Question at the back?
This approach seems to me like you've taken this standard approach to solving this problem with a factory function, splitting the factory function into context of the constructor, a static function, and the construct type machine wrapper or something. Would you care to explain what we get with this? Instead of just using one static factory function inside of our type, because we need to modify it. Adding this step.
Okay, so the question was is effectively what's the purpose of the construct stuff at all? No?
Why don't we just use a simple single static factory function inside of our file handler class? The usual approach which everybody did.
So the question is why don't we just use the standard, call the static initialization function directly? Factory function.
Which returns the expected type of error.
Okay, so the question is why don't we have a factory function that returns the item with stood expected? The reason is that that is not const_expr compilable, I believe, because any factory function of the kind that you're talking about is going to have to look something up at runtime and return something at runtime. This system works with const_expr. So that's the reason why. File handle clearly is something that can't do that, but I have other types which are 100% const_expr from start to finish, and those also return expected, and I want those to work, is the reason why. But you're right that if you didn't have that requirement, sure, use a factory function, have a stood map or a stood on order map underneath the bonnet. Question here.
In your example, you use pass type, it's a copyable object, yes? But for example, consider C++ where exceptions are totally disabled, so you cannot copy the pass without handling the error. How do we overcome this case?
I'm not sure if I entirely understand. I'll just try to repeat back what you said. You said that if C++ exceptions are disabled, then you seem to feel that which bit doesn't work?
No, when you try to copy the path and the copy may fail, how do you handle this case?
Okay, so the question is that if your C++ exception is disabled and you are copying the path and the copy of the path may fail, then how do you handle that? Well, you're in luck, because if that happens, that's not my problem. That's the standard libraries issue. And what happens in practice is that if it can't allocate new memory to store another copy of the path, it blows up and dies. So it's the same with all usage of the STL with C++ exceptions disabled. You are in pure undefined behavior territory an awful lot of the time. Anytime anything could fail, it simply kills the process.
Yes, in this case, when when the memory is gone, it's true, but instead of pass, it may be any other object which can fail during copying, not only because memory is empty.
Okay, so
it's maybe a problem.
So the point is that if there's any failure, and I think you're implying here an exception throwing failure, then that might hit built-in unreachable on Clang and GCC, which simply means that the compiler, the CPU, will run off the end of code that no longer exists, and you're going to start trampling all over the stack and killing your memory. Again, this is undefined behavior. If you turn off C++ exceptions, you are entering into a wild, wild world of fun with varying compiler-specific and STL-specific behaviors.
You said that still expected may be used in such environment. That's why I asked such question.
Okay, so the point is that stood unexpected can be used in a C++ disabled environment. Yes, but it comes with all of the same caveats and restrictions when used with other STL types that you would get whenever you have C++ exceptions disabled. This is one of the big advantages, perhaps, of using boost outcome. I know that almost all of boost is exactly the same, that it has issues with C++ exceptions disabled. But one of the ideas for outcome is it's going to go before study group 14, which is the low latency and embedded systems study group. And they're very keen on having C++ exceptions disabled. And it works very well. So you have a series of macro customization points. You have a series of free function customization points. You have lots of ways of intercepting when an exception would be thrown and doing something different, probably calls to terminate. But I don't know, you could log something, then calls to terminate. Or you could do something else. The point is that standard libraries work with C++ exceptions disabled as a convenience to the community, but the implementers don't make any guarantees with that. Any other questions? Okay. Okay, so as you all seem to have automatically gathered, you have this weird use of the parameters here rather than the end, and maybe Jonathan's got a better way of doing this, but I'll simply explain why I did it this way. My main use of this, you're not, it's a bit like the other gentleman said. If you're using, if you know the type that you're constructing, you're just going to call the static member function directly. If you're invoking it using this construct thing, you're probably in metaprogramming code where you have no idea the type that you're working with. So you're simply feeding everything through construct, including types that don't return expected and do throw exceptions and so on and so forth. So because of that, you're generally going to be passing around these objects between different layers of metaprogramming. And if you've written metaprogramming before, you'll know exactly what I mean here. But empty callable objects are the most useful kind of callable object that you can have. They are the easiest. So you simply hand off some callable object to other code. It calls the call operator. It gets out stuff. Now, as I mentioned earlier on, there's nothing wrong with moving your parameters from here over to here. So you now have two curly brackets followed by your parameters being here, and that's maybe a little bit more conventional. But what I would say is that I think, and maybe someone will correct me, but a variadic set of arguments is harder on the compiler than a non-variadic set of arguments. So I think that this construction will be slower to compile than this one. Anyone going to correct me on that? No? Good. Let's just assume it's true then. And if that's the case, then you'd want to choose this form. Now, the next question is that maybe someone's going to ask is, why don't I just use standard free functions? So what you'll find is that you can't partially specialize free functions. I personally really wish you could, but you can't. And there's a long list of reasons why you can't, but I just really wish we could anyway. So as a result, you have to use tag dispatching. So tag dispatching is when you put some initial template, some initial parameter type that basically selects the overload for you. The trouble with that form of dispatch is that when the compiler is compiling it, it has to make a list of all free functions that match construct, say. And there might be hundreds and hundreds and hundreds of them in a large code base. It then has to go off and do parameter matching. So it will look at the tag dispatch and it'll have to go off and match against those, which one of those overload sets to go and reduce it down to. And that's an awful lot slower than simply looking up a partially specialized type. Because it wasn't partially specialized, of course, it was fully specialized. So if the type is fully specialized, that can be hashed into a hash table, and the compiler can simply go, hash table, tell me what type I should be using here, and that's super duper quick. So that's much, much lower in compile times, is one of the reasons I chose it. Finally, free functions, because you have the tag dispatch, you have to type more, and I like to type less. I find visual complexity on the screen is one of my biggest problems with C++ as it is, especially STL-based C++. So avoiding that would be superb. Okay, any questions? Okay, in the middle.
Does this generate extra copies of your argument?
So the question is, Does this generate extra copies of your arguments? On C++ 17, I would be almost certain no. That's because you've got guaranteed copy elision. In C++ 14, I think the answer is occasionally. It depends on how you use it. As always, the more you type, the more optimal your code may come out. It's one of my great sadnesses, actually, that we can't make move construction, move semantics be default for all non-trivially copyable types in C++ now. I know it would break all the code really badly, but copy default semantics is really unfortunate. I know for C compatibility, you'd have to keep it for all trivial types, and that's fine. Trivial types, they're trivial. We don't care if we copy them. They're really elidable anyway by the compiler's optimizer. But for non-trivial types, if we could have them being move construction by default, that would be superb. And you might use a std copy to indicate when you want to copy something. That was obviously pure navel gazing. Ship's long sailed in that one. Question in the middle?
How to deal with several constructors with different parameters? In your example, you use only one constructor with pass type. For example, I can use several constructors with absolutely different types. How I specialize construct or something like this?
So the question is that how do you have different constructors with different parameters and have multiple overloads of the same? It's actually really simple. What you do is you add a constructor just underneath here with the different overload sets of the different ways that you can construct it. Then when you go to construct your construct file handle, that will unpack the arguments that you feed it into the ones that are stored in the member data, default initializing them as the case may be. You might want to replace some of these with optional, with the path optional with something else. That way then when your static member function comes and interprets it, it can see what the original overload set was. I did mention at the beginning that there was going to be a whole lot of extra typing, and I meant it. But yes, I have in my own code that exact issue where you have multiple constructor overload sets and you end up using optional to indicate which set it is, and then you're doing pattern matching effectively in your member function to figure out what the original overload was. It sucks. And if anyone can come up with something better, I'd all ears. At the back.
First, let me ask, are we now in the final one of questions? So, for generic questions, still expected or just about the construct?
Currently the questions... No, the questions are currently about this form of construction. We have more material to go. In the middle. Sorry, say again?
The pattern matching you just mentioned, like when you have multiple constructors and you do optional.
So the question is that if you have this system of having optional with a pattern matching of the different optional sets to figure out what the original overload was, the answer is yes, that would happen technically at runtime, but you will be amazed at what the compiler optimizer can do. So if it sees that there's only 3 different combinations, you'll find it just stamps out 3 different combinations, and it'll figure out the correct overload through inlining. Modern optimizers are amazing. Okay, so I'm not suggesting that this form of construction is the end-all and be-all. Different code bases have different requirements. Jonathan is probably going to teach me that this entire section was wrong, but that's okay. That's why I came here. Okay, so I'm kind of really surprised I got onto this with only 20 minutes to go, but there you go. This is my paper that I submitted to the meeting, WG21 meeting happening right now, and you'll probably be getting a bit of a flavor up until now of some of my issues with expected. I just want to clarify at the very beginning that I think expected should go into the standard. I think it should go in for C++20, even with some of the warts that are in it. Guy Davidson was saying to me that shipping is a feature, and I completely agree. I need this in sooner rather than later. I'm sure a whole lot of the rest of us do as well. So even if expected isn't what I would personally have done, it's probably good enough, and I'm happy. I don't see any showstopper problems with it. I just find things about it intensely irritating. So this is my list of issues. My first problem is it takes far too much typing to use. It's very verbose to use, and all of the operators and all the rest of this are just typing all the time. The second issue is that this is something that's so anodyne, but amongst Boost type people and standard library type people and WG21 people, there's a big pain in our heads about how the file system TS, the networking TS, and the newer TSs coming through have this dual error code design, which I'll show you some code illustrating the exact problem. And expected doesn't solve this, and we really would like it if it did. And by the way, outcome does. So Boost peer review came up with a way of solving it, and it's implemented. And you may find that Boost file system in the near future, if outcome is accepted, is going to start adopting this system to eliminate the dual error code problem. I know some people in the Boost community are very keen to get that gone, just because it annoys us. It makes us feel sick in our stomach. The other thing that really irritates me is that expected can throw exceptions. So the value observer can throw exceptions, and I have absolutely no idea what value that adds. It forces everybody using expected to write exception awareness, and that comes with costs. That's real development time costs. Developer cost at least $50, $60 an hour, and you are literally throwing cost onto the community for what I can see as no benefit. But I'll explain that shortly as well. My other issue with expected is that it has no stable ABI. I have been trying to argue on STUD proposals with the committee and members of the committee that I think a stable ABI would be really super duper important for this. And that lets big ARN users use it in their public interfaces, and everyone's going, oh, that's an implementation detail, and the C++ standard does not dictate implementation specifics on implementations. And I'm going, oh, just give me a stable ABI. Specifically, there's no C compatibility. That's really a type def, as it were, for a stable ABI, and I'll explain what I mean by that. And the last section here is it's underspecified what happens when library A talks to library B, and library A has one type of expected, and library B has a different incompatible type of expected. And I'll explain a little bit of that. So first thing is the verbosity. Here is an example of an open file function. So how this works is that we have some type opaque handle. We have some reference to a handle, which is some sort of smart pointer that points to it, and it manages a handle. If expected is successful, it will return a reference to a handle, otherwise it returns a STUD error code. By the way, expected used to default type E2 STUD error code, so you wouldn't have to, but the very latest edition of expected has removed that, so there's now no defaulting of E at all to anything. And the reason is not because anybody doesn't expect that almost all use cases for expected are going to be with STUD error code. It's because STUD error code really unfortunately drags in STUD string. And STUD string drags in all of the allocator machinery, all of the other fun stuff, and it really adds to compile times because it's literally hoisting in most of the STL. Because system error, very unfortunately, does that. So by eliminating the STUD error code defaulted parameter, you don't have to drag in system error, and therefore you can keep all of this stuff out. So that was felt to be better. But it doesn't mean that almost everybody who's using expected is going to be including system error and doing a template alias to alias in E as being STUD error code in their own code. There we go. Okay. So once again, if we open the path, if that fails, we return an unexpected. Again, here you have error code with system error category, exactly the same as before. We here are going to call some internal implementation using STUD no throw. People forget that new can be told not to throw exceptions. If it fails, it will return p equal to 0. It will also return set EC to some error code value. If it failed, here you have testing the P for null pointer. If it's failed, you call close. This looks very like C code, doesn't it? So you spend a lot of time in C having to sort of manually check, has something failed? If it has, you have to put sort of, little temporary constructors because there's no RIA in there. You sort of have to spell stuff out a lot. You hear down here, again, you're doing more tidy up. You're doing more of this, blah, blah, blah. Do you see what I mean by verbose? There's an awful lot of typing going on here. There's an awful lot of a feeling of you're stepping back in time, kind of. I don't want to have to type all of this stuff out. I want to just get to work. I mean, this is like C++ 20 we're talking here, right? I should just be able to knock something out real quick and it just goes fast. And this is one of the things I think that SG14, the low latency study group, have an issue with this as being a future low latency, lightweight error handling system, is that it seems a little retrograde. I mean, the great thing about C++ exception throws is that they're terse. You don't have to write anything. You don't have to look at anything. So having to spell all this stuff out in verbosity definitely seems like a step backward. But that's what I mean. It's very verbose. Oh, I've forgotten there was even another page. So this is an example of use of the very same file type that we just said before. And as you can see, there is, due to the lack of space, there's a pink more in here. So what we're doing here is we're comparing the error to a list of potential error values, and we're throwing the appropriate C++ STL exception type, which matches the failure cause. And this would have to be dumped out here probably into a function, which is all of this matching for you and throwing the appropriate things. And if it's none of those, you're then wrapping up into a system error and putting in error again. Again, this is all verbose. You're just typing all of this stuff out. It's all very brittle. I think we could do better than that. And this is the thing. This is what I think will actually turn up in people's code. So this is one of my issues. Okay, I promised I'd explain the dual error code system, the error code problem. So I've taken this straight out of the file system TS. These are two functions in the file system TS. I just chose copy file because it is nice and short. I put in the spec, which I pulled off of cppreference.com. You'll see here that there's a copy file. This is the throwing edition, so it copies file from this path to this other path, and it returns true if it succeeded. I don't know when it would ever return false and not throw an exception, I have to say, but I think that's the actual spec of the thing, so there we go. Either way, it will throw an exception if it failed. The specific exception type is file system error. It will usually be ec.message from to, and with the ec put at the end. So the ec is the error code, the internal one. And then, of course, it could be that you implement this using this and stuff in the paths as payload into the file system error exception type. So here's your trouble. You're having to write out two of these APIs for every single API in the library. You have to have an error code taking one and a throwing one. And that doubles the API count. And that's the kind of thing that gets library implementers feeling a little sick to the stomach. What we really want is a single API which returns expected that will throw the file system error with the message, with the payload of the path from, the path to, and the error code somehow automatically if you happen to go and talk to it the wrong way. But otherwise can be just as efficient as doing the standard error code thing that lets you use it without throwing any C++ exceptions. That's the ideal. And as I say, Outcome has an implementation that solves that, which was suggested during the Boost peer review. But Expected doesn't do this on its own. And I really wish it did, because that would solve a wart in the upcoming standard library. The forced exception awareness problem, I've kind of already talked about that already. This is kind of one of those weird things where the error observer, the pointer dereference observers, they're all narrow. So if you try to observe an error when there's no error there, you just get hard, undefined behavior. Usually you'll trash the stack, and you'll get memory corruption. And yet, weirdly, value is a wide observer. If you try to observe value, and notice that the star operator does exactly the same but without the wideness, it will throw this exception, bad expected access, with a copy of the E. Now, I just don't get this, and I said so in the paper that I sent it to WG21. What does this actually add? If the user really wants some exception to be thrown when value is not being observed correctly, they just bolt it on top. You simply inherit from expected into your own local expected type. You implement your own value observer. If it's not valued, you throw some arbitrary exception, and that solves the problem. So why are we building this into the standard library? Why are we forcing all users to have this semantics, to have to write exception-aware code, when we don't have to? And I don't get it. I don't even get why optional has it, actually. I don't know why they put throwing semantics in there. Just have it be undefined behavior. If users want more, they can define their own stuff. So I don't get that. This is the API stability problem. So big users of C++, They like to make components that they compile once, and then they have some shared library that just gets reused over time without being recompiled, often for years. I remember talking to someone in Microsoft who said that they've got some really critical library, and the only compiler they have that will compile it, because it's really, really ancient C++, is Visual Studio 6. So we're not even talking anything made outside the 1990s, right? And it's the only compiler that can compile the code because the code is just wrong. It's invalid C++. And the trouble is, none of the newer compilers can compile it, but that doesn't matter because we have this static library, and the ABI has unchanged between compilers from Visual C++ 1, 30 plus years ago, right up to the modern one. So you can still take this binary, you can still link against it, you can still work with it. So the ABI has been stable for that library, certainly since 96, 97, 98. And anytime they actually have to fix bugs in it, they have to pull out an old copy of Visual Studio 6 from like 1996 or something, and recompile it using that, and then reuse it from that. So ABI stability is really important for big, big users. There's a tool called the ABI Compliance Checker by someone Russian, whose name I can't remember. And it's an amazing tool for checking that your APIs have not changed and your ABI hasn't changed. So you can run that as your Travis or your CI job, and it will say you changed something which broke ABI. And it's an amazing tool. It's really, really handy. Most of the big corporations I've worked in employ that. And anytime you break ABI, you get a slap in the wrist and told you cannot commit this until you fix it. The other issue is that if you have a super duper large code base that has like hundreds and thousands of files, each of which have to be compiled, you really compare about the stuff that you're including. I mean, you really, really, really compare about it. I've worked on teams where you are not allowed to add and include without having managerial approval. So if you typed in a new include, which wasn't on the whitelisted manifest of includes for that particular file, it would refuse to commit. You couldn't submit it to source code control. And you'd have to get your manager to sign a bit of paper to say that you could. And that usually meant the entire team had to audit it. That's how much they care, because if you put in an extra include that affects build times, and you're compiling, you know, hundreds of thousands, if not millions of comp plans, that can be a huge impact to the entire company. So it's something you just can't do. Because of this, and I mentioned the Google style guide earlier on, usually you can't use the STL in any of these public APIs. Public APIs certainly can't throw any exceptions. Often they're actually written in C. In fact, the contract with the last one, the entire API was C, public API, but all the internals were using C++. Nobody on the outside could tell it wasn't a C library. Examples of these regulations: Microsoft Com can't use STL in the public things. It's still C compatible, even to this day. Qt, no STL, no non-fatal C++ exception throws, although it's better than it used to be. It used to be that if you threw C++ exceptions through Qt code, all sorts of horribleness happened. Now, I think it's just a case of it shouldn't be too bad, but they still say in the documentation you should really quit the program. And the Google C++ style guide bans most of the STL, most of Boost. There's a list of things you're allowed to have, and you can't do any C++ exception throws. So I'm going to say this. Is Expected going to get into those public APIs, those big iron users who have a real need for returning failure in a consistent fashion, but can't throw exceptions? No, they're not going to use Expected, because it's part of the STL. There's no ABI guarantees. You have no idea if this thing's going to be usable into the future, and it's going to break your ABI, so you're just not going to use it. And I feel that's a huge missed opportunity, not least because it's really trivial to get Expected to talk to C code. Outcome has a C interface. So if you're in C code, and you're talking to some C++ that's returning an outcome, there is an API from your C code that you can just work away with that. You can call directly to C++ code, which was returning outcomes, and you can work with that. There's a C preprocessor macro API for working with it. So C code can call C++ code. And that means Python, which can speak C, can call C++ code. It means Rust, which can speak C code, can call C++ code. There's a long list of really good interoperation benefits that are just there waiting to be grabbed. But without stable ABI, we can't do any of that. So I'm getting now to the end of my time. I'm going to stop here. There's a reason why I'm going to stop here, and that's because this section of ABI interoperation has been underspecified. This is true. However, outcome is not hugely better on this yet. I can talk about it, but I couldn't give you an answer that was conclusively why it was the case. All of the stuff I've said in this presentation up until now, I have answers. They may not be the right ones, but I have answers which will make the problem better in outcome. This, I have something I'm not sure of yet. I'm actually working on it right now, which is why I was refactoring the implicit construction API and the converting API of outcome. So the tutorial section on outcome, which shows the end of this, I will finish probably about a week or two from now. So if you had me come and do this talk then, I would be happy to talk about this. And if you go to the ACCU talk, assuming they let me in, I will almost certainly be talking about this a whole load, because ABI interop, basically, the problem is when library A has one form of expected, so it has one type of error, and library B has a different type of error. And then if you're in your application and you're using one of the libraries, library B, and you're calling into library A, then, oh dear, I have error of two different types, and I can't interoperate them because they're two totally separate types. Do I have to put a switch statement in here? Do I throw an exception? What do I do? And I have, I think, a solution for that, more or less, but it's not fully baked yet. So I am just not going to mention any more of that. So that's the end of my talk. When Jens said you really need an hour and a half for this stuff, I was like, yeah. I hope it wasn't too boring. Thanks very much. Okay, I've been asked to remind that there are a microphone in the middle if anyone wants to ask any questions. You've probably been asking questions throughout, but rock on. Sorry, so the question was, will I be sharing the slides? I think Jens will be sharing the slides for all of the talks here. So yes, they will go online.
Okay, it's working now. At the beginning of your talk, you were mentioning about the overhead of exceptions. And you showed the benchmark, the runtime benchmark, the overhead. What I think is missing there is also the bloat overhead, or the binary size overhead. For some reason, that's still significant. Even when you switch to error codes, in a sense you're doing it manually, your binaries are measurably smaller than when you use exceptions. I experienced that with all compilers, and it's significant. Today people usually ignore this, but I think that C++ as a performance-oriented language should care about that. The standard committee, it should care about that. And this brings me to the second question. The problem you mentioned here is the dual API. The problem during your proposals of, I think it was outcome V1 on Boost, I did some questions about that because I was implementing my own solution. And now I'm currently lost from the debate, so I'm going to ask you how you solve that in outcome. Because I think it can be solvable in a way that you get exceptions or error codes, as you mention it, in a safe way if only one thing is added to the language, which is R-value overloads of destructors. So imagine if you return stood expected, and you leave it untouched, unexamined, then the compiler would invoke the R-value overload of the destructor, and it would throw an exception. Otherwise, you'd save it into a local variable. So it will the thing the stood expected would only have R-value overloads of all of its functions. So when you return from a function, you would have the option of either ignoring it, not touching it, in case the ampersand destructor would check if there's an error and throw. Otherwise, you'd have to save it into a local variable of some other type, convertible from the stood expected. And then you'd use it like an error code. So my question is, could you elaborate a bit on how you solved it in outcome? Because I think it's really important. It's coming into the language and it should be solved properly.
Okay, so I gathered out of that 3 points. I don't know if I have to actually repeat. If the microphone's able, I'll repeat them back anyway, just so I got them all. The first one was about code bloat that comes from table-based exceptions. The second one was about the performance benchmarks should be updated to include that, wasn't it? And then the third one was about destructors.
How did you solve the dual API thing?
Yes, okay.
What's your proposal for that?
Okay, so I'll start with the first one. The first one is that performance benchmark is completely unreliable and nobody should take it seriously. I had some feedback of JF Bastian about why don't I do a whole lot of more benchmarking on all of this, and I said because I do not have infinite resources like, say, Bloomberg do. So when they had to go off and prove allocators, they were able to throw men and compute time at it to come up with a statistical proof. I think to prove this, you need a statistical proof as well, to do a real conclusive proof for this stuff. And I'm one guy. I don't have the time to do that. I had strongly suggested to anyone who does have that kind of deep pockets and money that they should. Otherwise, I think you should just drop the performance argument. So sure, anyone who's used these things knows that they are extremely fast. They solve a whole lot of performance problems, but proving it is enormously difficult without having to spend an awful lot of time invested in it. So my argument is don't use the performance argument. If you're going to start with the performance argument, you're going to get a whole lot of people saying prove it, prove it, prove it, and you can't prove it without investing 6 months of your time doing benchmarks. So I'm not going to go down that route. Other people can if they want to. So that's the first one.
Sorry, does showing them codegen ever work?
Sorry, say again?
Does showing those people who are unconvinced, does showing them codegen, is it ever convincing for them? Because you don't have to measure it, you can simply show them codegen. The assembly that you get from one way or the other way, it's like this or this.
You say about the code gen, but you'd be amazed how much bike shedding can happen over code gen. And then people say, well, a different version of the compiler does different code gen, and it just devolves into non-productive discussion. Performance is just something I have found to not bother talking about. You can talk about it at the bar, but once you get into committee peer review situations, it just devolves into non-productive discussion. I mean, John Lakos had to do an enormous amount of statistical proof to prove allocators. You've probably seen his swirling heat maps in his stuff, and that's what you get when you can throw dozens of people at it and a whole lot of cloud compute time, because Bloomberg's rich. So it needs someone like that to prove this stuff statistically. So I just don't go down that route. I'm happy to discuss stuff in the bar, though, and we can all have our opinions on things, even people who are completely wrong. I respect their opinion. They're often really expert people who are just completely wrong about this stuff, but proving it is really hard. So that's the first thing. The second thing there was you were asking about how I had solved the dual error code problem with outcome. So obviously this is not a talk about outcome. And by the way, I didn't invent it. I simply followed the Boost peer review advice of what to do to solve the error code problem. So the way that outcome does it is that I just expected a whole load of hassle for throwing exceptions out of its observer functions. You'd be glad to know that outcome also throws exceptions out of its observer functions, but the difference is that they're programmable. So you can come along and you can say that for this specific instantiation of outcome with these specific types, when called from a certain namespace or not, as the case may be, you have a whole load of knobs and buttons to go and twiddle on that, or when it's interfacing between one namespace and another namespace, then you can set up custom programmed behaviors to say that I want to throw a certain custom exception or call some custom routine, or in the case of file system, throw a file system error. So this is the way we implemented it. You simply come along, you say that for all expected outcomes that are returned by the file system library, if they are ever observed without a check beforehand where the observation is incorrect, then we're going to throw a file system error with the paths embedded into it, and you'll get exactly the same outcome with the same file system error exception being thrown with all of the same metadata as you would if you had the existing throwing overload. So if you want to know a little more about that, if you go to the outcome tutorial, there's an entire dedicated section on that, and it takes you very slowly, step by step, of how that works, and that's the quickest way of doing it. For the third thing, you were suggesting there about R-value destructor overloads. Now, I am highly sympathetic, personally, to that argument, but the Boost peer review was not. So they were very clear that throwing any form of exception from any form of destructor was something that they would consider a deal breaker for a library to get into Boost. I think that's a very conservative approach, but I can see where they're coming from. Now, you suggest that if the language were changed to add R-value destructor overloads, and I think we're now into a new category of situation, because there's no existing code written using these R-value destructors, so therefore there's no existing code that's going to get broken by us deciding that R-value destructors are going to be this particular semantic or have this ability to them that they might throw exceptions. I would wonder to myself, though, because throwing exceptions from destructors, it's something I used to do when I was about 22 years old in my C++ that I used to write back then. I was like, oh, we can have nest exception throws and we can have this cool machinery that when you throw an exception while handling an exception, instead of aborting the process, we're actually going to attach this new exception onto the bottom of the currently thrown exception, and we're going to build a chain of exceptions. And of course, this is now built into the C++ 11 STL, so there's a nested exception type, and you can attach a long chain of exceptions. But I'll tell you something, I think that was really cool stuff to do when I was 22. I haven't really ever been tempted to do it since in any of the code I've written. So I would wonder if that is not a solution in search of a problem. And I would need to see evidence to prove that I'm wrong on that.
I think it's easily provable that in the case of R-value destructor overloads, all the naysaying about throwing exceptions from destructors doesn't apply there, because it can never happen in a situation where there's an exception already in flight, because that destructor will be called after a successful function call. So simply all the arguments don't apply for that particular situation.
If you can guarantee that your R-value destructors would never get thrown, as in you write it into the standard, will never get thrown during, or called during a destructor unwind, then I think I could get on board with that. The session's over, I'm afraid, so thank you very much for being here, and I'm here for questions after.